before a single electric bulb ever glowed against the darkness, before the hum of dynamos shook the floors of industrial buildings across a continent, the world that made Thomas Edison possible already existed, a world of canal mud and river cold, of oil lamp amber and telegraph percussion, a world that pressed itself into the mind of a child and never fully let go. The northern Ohio flatlands of the 1840s stretched in every direction with an almost oppressive horizontality. The sky dominated everything vast, grey-blue and indifferent, pressing down on a landscape of hardwood forest and recently cleared farmland, of black soil turned by iron ploughs, of creek beds running brown with spring runoff. In this broad, unhurried country, small towns had taken root along the waterways, their modest ambitions expressed in brick storefronts and timber frame warehouses, in the careful geometry of courthouse squares and the muddy informality of back lanes. Milan, Ohio, was one such town, and in 1847 it was briefly, improbably, one of the busiest grain shipping ports in the entire United States. The Milan Canal connected the town to the Huron River and from there to Lake Erie, and along this narrow, engineered waterway moved an extraordinary volume of commerce. Grain barges moved with the slow deliberateness of working animals, their flat hulls riding low in the water beneath the weight of wheat and corn harvested from the surrounding farms. The loading docks along the canal basin were perpetually active during the shipping season. The mechanical clatter of hoisting equipment, the shouts of dock workers, the grinding of wooden hull against stone wharf. The smell of the place was particular and unmistakable. River mud and raw grain, horse sweat and hemp rope, the faint sulphurous edge of the coal smoke rising from the small foundries at the edge of town. In winter, the canal froze, and the ice that locked the waterway each February fractured in great grey-white plates when the thaw came, grinding and shifting with a sound like distant artillery. On Choate Street, set back from the canal district on a modest rise, stood the Edison family home. It was a two-story brick structure of unpretentious design, green shutters framing its windows, a wide front porch overlooking the dirt lane, the kind of house that expressed solid working-class respectability without any aspiration toward grandeur. Samuel Edison, Thomas's father, had built it with his own hands, and the house bore the marks of that practical construction: slightly uneven window frames, a porch step that creaked under weight, the particular solidity of brick laid by someone who understood the material intimately. The kitchen sat at the rear of the ground floor, and beneath it a root cellar descended into the cool earth, its shelves lined with preserved vegetables and glass jars, its stone walls perpetually damp. It was in this cellar, according to family accounts, that the youngest Edison first began experimenting with chemical compounds, drawn by some early instinct toward the transformative properties of ordinary substances. Thomas Alva Edison was born in this house on February 11, 1847, the seventh and youngest child of Samuel and Nancy Edison. He arrived into a world that was, by any measure, pre-modern in its fundamental character. The light that illuminated the rooms of the Choate Street house came from oil lamps, their amber pools warm and intimate, but limited, casting deep shadows into corners, requiring constant attention and maintenance, filling the air with a faint, oily smoke. The world beyond the lamp's reach was genuinely dark in ways that have become almost impossible to imagine. The darkness of a rural Ohio night in the 1840s was absolute, broken only by starlight and the occasional distant glow of a neighbor's window. Milan's prosperity proved fragile. When the railroad bypassed the town in the early 1850s, choosing a route that left Milan's canal infrastructure suddenly obsolete, the economic logic that had made the town briefly significant evaporated with remarkable speed. The grain barges slowed and then stopped. The loading docks fell quiet. Families who had built their livelihoods around the canal trade found themselves stranded in a backwater watching commerce migrate to the iron rails that now defined the geography of American economic life. Samuel Edison, practical and restless, recognized the situation clearly. In 1854, when Thomas was 7 years old, the family relocated north to Port Huron, Michigan. Port Huron occupied a different register entirely. Where Milan had been a canal town of agricultural commerce, Port Huron was an industrial lakeside settlement of rougher character, a place where the St. Clair River ran cold and grey between the Ontario and Michigan shores, where lumber mills and foundries announced their presence through noise and smoke, where the working waterfront had none of Milan's brief gentility. The river here was wide and purposeful, carrying Great Lakes shipping traffic in both directions, its surface broken by the wakes of steamers and the slower passage of timber rafts. The smell of the place was different from Milan: sawdust and cold water, machine oil and coal smoke, the particular metallic edge of a town built around iron and steam rather than grain and rope. The Edison family settled in a substantial house on the outskirts of town, and young Thomas was enrolled in the local one-room schoolhouse. The physical environment of that schoolhouse has been described by those who knew it: cracked plaster walls, a single wood-burning stove that heated the room unevenly, the smell of chalk dust and damp wool coats, the particular acoustic quality of a room full of children reciting lessons in unison. Edison's tenure there was brief. His mind moved in directions that the schoolroom's rigid structure could not accommodate, and his mother Nancy, herself a former teacher, withdrew him from formal education and took over his instruction at home. The schoolhouse's loss became the world's gain, but it was the Port Huron train depot that would prove most consequential. The Grand Trunk Railway operated through Port Huron, and the depot was a place of constant sensory intensity. Iron rails gleaming in early morning frost, the sulphurous plume of steam engines building pressure before departure, the rhythmic percussion of telegraph equipment clicking in the station master's office. That telegraph sound was everywhere in the depot, a constant Morse code undercurrent beneath the noise of arriving and departing trains, and it lodged itself in Edison's consciousness with particular force. The telegraph represented something new and almost miraculous in the mid-19th century landscape. The transmission of information at the speed of electricity, the collapse of distance into instantaneous communication. For a boy already drawn to the properties of chemicals and the behavior of physical systems, the telegraph was a revelation. At 12 years old, Edison obtained permission to sell newspapers and candy aboard the Grand Trunk Railway trains running between Port Huron and Detroit. The daily journey along this corridor, roughly 60 miles of Michigan countryside passing outside the train windows, became his mobile classroom. He read voraciously, acquiring newspapers and books from the Detroit Public Library during his layovers in the city, consuming them on the return journey. He also negotiated the use of a section of the baggage car, converting it into a rolling laboratory where glass bottles of chemicals and lengths of copper wire rattled against each other with the motion of the train. The Grand Trunk Railway corridor thus became something unprecedented, a moving experimental space threading through the Michigan countryside, its young occupant conducting chemical experiments between station stops, surrounded by the smell of coal smoke and the rhythmic percussion of iron wheels on iron rails. The landscape through which that train moved, the flat Michigan farmland, the occasional small town with its water tower and grain elevator, the frozen creek beds in winter and the green fields in summer, was the backdrop against which Edison's earliest intellectual formation took place. It was a landscape defined by the technologies of its moment: the canal giving way to the railroad, the oil lamp beginning its long retreat before the advancing claims of gas, and eventually electricity. Edison was born into one technological world and would spend his life building the next one, and the physical environments of his childhood: the canal town, the industrial river port, the railway corridor, were the first classrooms in which that lifelong education began. The world before the light was not a world of absence. It was a world of particular textures and specific smells, of amber lamp glow and river cold, of telegraph percussion and steam engine thunder. It was a world that pressed itself into the senses of a curious child and created the conditions for everything that followed: the laboratories, the patents, the inventions that would eventually illuminate the darkness that had defined every human night since the beginning of recorded time. In the years before Thomas Edison became the most famous inventor in the world, he was something far more ordinary and far more essential. A young man adrift in the industrial corridors of mid-19th century America, moving from city to city with a battered toolkit and an insatiable appetite for understanding how electrical systems worked. Those wandering years, stretching roughly from 1863 to 1868, left no monuments and generated no headlines. But they forged, in the particular crucible of the telegraph office, a technical mastery that no formal education could have replicated. The telegraph operator's world was a sensory environment unlike any other in the 1860s. Step inside any Western Union office along the American Midwest or Eastern Seaboard during those years, and the atmosphere announced itself immediately. The cramped dimensions of rooms carved out of railway depots and commercial buildings, the walls lined with Morse code charts and wiring diagrams tacked over plaster that had yellowed with age and tobacco smoke. The dominant sound was the sounder key, its rhythmic percussion filling the room with a constant mechanical conversation, dots and dashes, arriving and departing in overlapping streams, each operator translating the electrical impulses into language with the practiced ease of a musician reading notation. The smell was equally distinctive. Hot insulation and machine oil, the acrid chemical tang rising from battery rooms where glass jars containing zinc and copper electrodes sat submerged in sulfuric acid, their electrochemical reactions generating the current that powered the entire system. Those battery rooms deserve particular attention because they represented the most intimate interface between the telegraph operator and the underlying science of electricity. The jars, sometimes dozens of them arranged in long rows on wooden shelving, were fragile, temperamental, and demanding of constant maintenance. The acid ate through metal contacts and wooden shelves alike. The zinc electrodes dissolved gradually as current was drawn. The connections between jars required regular inspection and cleaning. For a young operator with genuine curiosity about electrical phenomena, the battery room was an education in applied electrochemistry conducted in real time, every shift, in every office across the country. Edison moved through this world with a restlessness that his contemporaries sometimes found difficult to understand. After his years on the Grand Trunk Railway corridor, he had learned telegraphy from a station agent named James Mackenzie, whose son Edison had reportedly pulled from the path of a runaway freight car. A story that has taken on the quality of legend, but reflects the informal, favor-based economy through which technical knowledge circulated in that era. By 1863, Edison was working as an itinerant telegraph operator, and the geography of his wandering traced the nervous system of industrial America. Cincinnati presented itself as one of the great commercial cities of the interior, its waterfront district along the Ohio River, a dense, gaslit landscape of saloons and boarding houses, commission merchants and steamboat offices, the smell of river mud and coal smoke hanging permanently over the lower streets. The telegraph offices here served the commercial traffic of a major inland port, handling commodity prices and shipping information, the constant flow of commercial intelligence that made the telegraph indispensable to 19th century business. Edison worked in Cincinnati's offices during this period, absorbing not just the technical demands of high-volume message traffic, but the organizational logic of a large telegraph operation. The hierarchy of operators, the management of multiple simultaneous circuits, the physical infrastructure of a major relay station. Louisville followed, its telegraph exchange humming with the industrial energy of a border city that had grown wealthy on river commerce and was now reorienting itself around the railroad. The offices there occupied the upper floors of commercial buildings along the main business district, their windows overlooking streets where horse-drawn wagons competed with the early infrastructure of urban rail transit. The winter cold in Louisville penetrated the telegraph offices with particular persistence. The cast iron stoves that heated the instrument rooms were never quite adequate, and operators worked in their coats during the coldest months, their breath visible in the air above the sounder keys. Detroit appeared repeatedly in Edison's wandering itinerary, and the city held a particular significance in his intellectual development. Working night shifts in Detroit's telegraph offices gave him access to something he valued more than sleep, the early morning hours when the message traffic slowed and the instrument rooms fell quiet. Edison used these hours to read, acquiring books from the Detroit Public Library and working through them with systematic intensity. The physical environment of those early morning reading sessions, the gas jets hissing softly overhead, the sounder keys silent, the winter streets of Detroit empty and dark outside the frosted windows, was the environment in which Edison's self-education reached its most concentrated form. He worked through scientific texts that most formally educated engineers of his era had never encountered, absorbing the theoretical foundations of electrical science alongside the practical knowledge he was accumulating at the instrument bench. The Western Union offices of this era were, in their physical construction, remarkable environments of early industrial infrastructure. Their high ceilings were strung with copper wire in various states of organization, main trunk lines running in neat bundles along the ceiling joists, branch circuits dropping down to individual instrument positions, the whole system representing a visible map of the electrical connections that linked each office to the broader network. The instrument tables themselves were scarred with years of use, the wood darkened by machine oil and hand grease, the surfaces marked with the circular impressions of battery jars and the scratches of metal tools. Each operator's position was a small personal territory, the arrangement of instruments reflecting individual working habits developed over years of practice. The technical demands of first-class telegraphy were considerable. A skilled operator could receive and transcribe messages at rates that required sustained concentration and physical coordination, the fingers moving across the key with a rhythm that experienced operators described as almost musical, the mind simultaneously translating incoming Morse code into language while composing outgoing messages. Edison was, by multiple accounts, an exceptionally skilled operator, capable of handling the fastest transmission speeds then in use. But his real distinction was not speed. It was the habit of mind that led him to question why the systems worked as they did and to imagine how they might work better. The physical evidence of this questioning habit appeared in the margins of his notebooks and on the scraps of paper that accumulated around his instrument positions, sketches of circuit modifications, calculations about battery efficiency, diagrams of relay configurations that might improve signal clarity over long distances. The telegraph office was simultaneously his workplace and his laboratory, and the boundary between the two was never clearly defined in Edison's practice. Boston in 1868 represented a different order of environment entirely. Edison arrived in the city at a pivotal moment in his development. He was 21 years old, possessed of extraordinary practical knowledge and a growing theoretical foundation, and Boston was then the most intellectually sophisticated city in America. The scientific and intellectual atmosphere of the place was palpable in its physical landscape. The bookshops along Washington Street, where the latest scientific publications from Europe and America were available, the reading rooms of the Mechanics Institute, where working men with technical interests could access journals and reference works, the cluttered electrical supply shops near the waterfront, where components and instruments could be purchased or examined. The Boston Telegraph Office, where Edison found employment, was operated by the Western Union subsidiary serving the city's commercial district, and it occupied premises that reflected the relative prosperity of a major northeastern business center. The instrument rooms were larger and better equipped than the Midwestern offices Edison had known, the message traffic heavier and more demanding. But it was the after-hours environment of the office that mattered most, the late-night silence of the instrument room after the commercial traffic had subsided, the gas jets hissing softly overhead, the city outside the windows quieting toward midnight. It was in this environment that Edison's first patent took shape. The electric vote recorder, a device designed to allow legislative bodies to record votes electrically rather than through the slow process of oral roll calls, was conceived at a wooden workbench in the Boston Telegraph office, copper filings scattered across its surface, the smell of rosin flux mixing with the chemical tang of the battery room. The device itself was straightforward in its electrical logic, a direct application of telegraph technology to a specific administrative problem. Edison filed the patent in 1869, and it was granted, his first of what would eventually become more than 1,000. The vote recorder found no buyers. Legislators, Edison was informed, had no interest in speeding up the voting process. The deliberate pace of roll call votes served important political functions that an electrical shortcut would undermine. It was a lesson that lodged permanently in his thinking. Technical elegance meant nothing without a market willing to receive it. From that point forward, Edison's approach to invention would be shaped by a relentless attention to practical utility, to the question of whether a device solved a problem that people actually needed solved. The Boston years ended the wandering phase of Edison's life. He had moved through the industrial corridors of mid-19th century America and absorbed everything they had to teach: the electrochemistry of battery rooms, the signal physics of long-distance transmission, the organizational logic of large telegraph networks, the commercial realities of a technology-dependent marketplace. The telegraph had been his university, its offices his laboratories, its circuits his textbooks. What came next would require a different kind of environment, one that Edison would have to build himself from the ground up according to his own specifications. The architecture of that environment and the extraordinary work it would make possible waited just a few years ahead in a small New Jersey town called Menlo Park. There are places in history where the future arrives ahead of schedule, where the ordinary logic of time and geography seems briefly suspended, and something genuinely new enters the world. In the winter of 1876, one such place was a modest cluster of white clapboard buildings rising from the frozen farmland of central New Jersey, visible at night from miles across the dark countryside as a blaze of carbon arc light against the rural darkness. Menlo Park was not a city, not a university, not a government installation. It was something the world had never quite seen before, a private industrial laboratory built for the systematic, deliberate production of invention itself. The New Jersey landscape that surrounded it in early 1876 was emphatically rural. The terrain rolled gently through low winter hills, the fields brown and frost-hardened between stands of bare oak and hickory, the unpaved roads reduced to frozen mud ruts by the alternating freeze and thaw of a mid-Atlantic winter. The Pennsylvania Railroad line cut through this countryside with the purposeful geometry of industrial infrastructure, its twin iron rails gleaming in the pale winter light, its telegraph poles marching in regular intervals across the fields, the distant percussion of a passing locomotive audible long before the train itself appeared on the horizon. The nearest town of any consequence was Metuchen, several miles distant. The isolation was not accidental. Edison had chosen this location with deliberate care, selecting a site close enough to the railroad for practical access to New York and its supply networks, but far enough from urban density to allow the kind of focused, uninterrupted work that his ambitions required. The Menlo Park compound took shape through 1876 with remarkable speed. At its center stood the main laboratory building, a two-story white clapboard structure approximately 100 feet in length, oriented along a gentle rise in the terrain, its tall windows facing in multiple directions to capture maximum natural light during the working day. The building's exterior was plain to the point of austerity, its white paint already beginning to show the weathering effects of New Jersey winters, its wooden steps worn smooth by the constant traffic of workers, experimenters, and the occasional journalist or investor making the journey from New York to witness whatever Edison was working on that particular week. The ground floor of the main laboratory was the operational heart of the entire compound. Chemical shelves lined the walls from floor to ceiling, holding hundreds of labeled bottles arranged with a librarian's systematic attention. Acids and alkalis, metallic compounds and organic solvents, the raw material inventory of a working experimental chemistry operation. The labels were written in various hands, reflecting the contributions of the multiple assistants who maintained the chemical stocks, and the bottles themselves ranged from small pharmaceutical vials to large glass carbis containing bulk quantities of frequently used reagents. The smell of the ground floor was complex and persistent. The sharp bite of acids, the organic sweetness of certain solvents, the metallic undertone of compounds containing copper and iron, all of it layered over the baseline smell of wood and machine oil that permeated every surface. The central work tables of the ground floor bore the physical record of years of experimental work in their surfaces. The wood was scarred with acid burns where spilled reagents had eaten into the grain, marked with the circular impressions of battery jars and glass vessels, scratched by the movement of metal instruments and mechanical components. Soldering marks darkened the table surfaces near the electrical work areas, and the accumulated residue of hundreds of experiments had given the wood a particular patina. Dark, complex, and somehow expressive of the intensity of activity that had taken place there. Gas pipes ran along the ceiling, dropping at intervals to supply the burners used for heating chemical reactions, and electrical wiring in various states of completion was strung between the gas pipes and along the walls, the whole overhead infrastructure of the laboratory representing a visible map of the experimental work in progress at any given moment. The upper floor of the main building housed the library and drafting room, and the atmosphere there was markedly different from the chemical intensity of the ground floor. Bookshelves groaned under the weight of scientific journals from Europe and America, publications in English, French, and German, their spines showing the wear of regular consultation, their pages marked with pencil annotations in Edison's distinctive hand. The collection was not merely decorative. Edison used it as a working research tool, directing his assistants to search the literature before beginning work on any new problem, establishing what had already been attempted and where the unexplored territory lay. Large drafting tables occupied the center of the upper floor, their surfaces perpetually covered with schematic drawings in various stages of completion. Circuit diagrams, mechanical sketches, the visual language through which experimental ideas were translated into buildable objects. Adjacent to the main laboratory stood the machine shop, and this building operated according to a different sensory register entirely. The rhythmic turning of metal lathes filled the space with a sound that was almost musical in its regularity. The steady rotation of the cutting tool against the workpiece, the fine spiral of metal shavings accumulating on the floor below. Grinding wheels threw showers of orange sparks that arced through the air and died against the wooden walls, leaving small scorch marks that accumulated over months into a kind of unintentional decoration. The smell of hot metal and cutting oil was pervasive, a sharp industrial scent that clung to clothing and skin. The walls of the machine shop were hung with precision measuring instruments, calipers and micrometers, gauges and templates, their careful arrangement reflecting the understanding that accurate measurement was the foundation of reliable experimental work. The machine shop's capabilities were central to Edison's method. The ability to fabricate custom components on site without waiting for outside suppliers compressed the experimental cycle dramatically. When a new idea required a specific mechanical configuration, the machine shop could produce it within hours. When a component failed and needed modification, the lathes and grinding wheels could rework it immediately. This integration of fabrication capability with experimental work was one of the genuinely novel features of the Menlo Park approach. The laboratory and the workshop were not separate institutions, but a single integrated system, their physical proximity enabling a speed of iteration that no previous inventor had enjoyed. The other structures of the compound each served specific functions within this integrated system. The carpenter's shop produced the wooden housings and structural components that many experimental devices required. its interior fragrant with fresh-cut wood and sawdust, its workbenches lined with hand tools arranged with the same systematic attention that characterized the chemical shelves in the main laboratory. The carbon shed was a rougher, darker space, its walls and floor stained black with the carbon compounds that Edison's experiments increasingly required. Carbon being a material of extraordinary experimental importance in the development of both the telephone transmitter and, later, the incandescent light bulb. The glass-blowing facility occupied its own small building, its furnace the dominant feature, a source of intense radiant heat that made the space uncomfortable in summer and welcome in winter, the molten glass glowing orange and white as the glassblower shaped it into the specific forms that experimental work demanded. The office building stood slightly apart from the main laboratory cluster, and its function was administrative rather than experimental. The management of correspondence, the preparation and filing of patent applications, the financial accounting of a research operation that consumed resources at a rate that required careful attention. Patent applications were a constant output of the Menlo Park operation, and the office building processed them with the efficiency of a small legal practice, the paperwork of invention moving through its rooms in steady streams. The physical connective tissue of the compound was a wooden boardwalk that linked the buildings, raised slightly above the ground level to provide passage across the muddy terrain that characterized the site during wet weather. This boardwalk was a practical solution to a practical problem. The New Jersey clay soil became impassable mud in rain and thaw, but it also gave the compound a particular character. The sound of footsteps on wooden planking marking the movement of workers between buildings throughout the working day and frequently well into the night. A vegetable garden occupied a portion of the property, its seasonal produce supplementing the diet of the workers who lived on site. A well provided water. A stand of oak trees at the property's eastern edge offered shade in summer and a windbreak in winter. At night, the Menlo Park compound presented a spectacle that had no precedent in the rural New Jersey landscape. Carbon arc lights illuminated the laboratory interior with a harsh blue-white brilliance that spilled through the tall windows onto the muddy lane outside, casting sharp shadows across the boardwalk and the surrounding ground. This light was qualitatively different from anything that oil lamps or gas jets could produce. More intense, more white, more industrial in character, the light of the future arriving in the present tense. It was visible for miles across the dark countryside, a beacon of concentrated human activity burning against the rural darkness, and it drew visitors and curiosity in roughly equal measure. Farmers on the roads between Metuchen and Menlo Park reported seeing the light from considerable distances, a strange brightness on the horizon that had no natural explanation. The workforce that populated this environment was itself a deliberate construction. Edison recruited with attention to specific technical capabilities, machinists of exceptional skill, chemists with both theoretical knowledge and practical experience, glassblowers capable of producing the precise shapes that experimental work required. According to Paul Israel of the Thomas Edison papers, there was something about Edison that seemed to embody a particular vision of American inventive genius, self-taught, direct, simultaneously down-to-earth and visionary. That quality attracted talented people who might otherwise have sought more conventional employment, and the Menlo Park Laboratory became, in the late 1870s, a concentration of technical talent that had no equivalent anywhere in the country. The compound as a whole represented a new idea about how invention should be organized, not as the solitary activity of an isolated genius working in a private workshop, but as a collaborative industrial process conducted in a purpose-built environment, equipped with every tool and material that experimental work might require. The architecture of Menlo Park was the architecture of that idea made physical. Its buildings, its equipment, its chemical shelves and machine tools and glass-blowing furnaces, all expressing the conviction that the systematic application of human intelligence to technical problems, given the right environment and the right resources, could produce results on demand. What those results would be in the extraordinary years that followed would justify that conviction beyond any reasonable expectation. In the autumn of 1877, something happened inside the Menlo Park laboratory that no human being had ever witnessed before. A machine spoke, and then repeated exactly what it had said. The moment was so improbable, so far outside the boundaries of what the era considered technically possible, that the man who built the device reportedly could not quite believe it himself. The world was about to meet its first recording, and the environment in which that meeting took place was as particular and atmospheric as any cathedral or battlefield. A cluttered, chemical-smelling, gas-lit laboratory in rural New Jersey, where the future arrived without ceremony. Late autumn had settled over the Menlo Park compound with its characteristic grey persistence. The oak trees at the property's eastern edge had shed their leaves, and the wooden boardwalk connecting the laboratory buildings was slick with morning frost that lingered in the shadows until midday. Cold air moved through the gaps in the main laboratory's clapboard walls, not dramatically, but persistently, the kind of infiltrating chill that required workers to keep their coats nearby, even when the interior gas burners were running. The windows were fogged with condensation, where the warm interior air met the cold glass, and the light that filtered through them in the short November afternoons was thin and grey, supplemented by the hiss and glow of the gas jets overhead. The workbenches of the main laboratory in this period were cluttered with the particular material evidence of the phonograph's development. Tin foil cylinders of varying diameters occupied one section of the central table, their metallic surfaces dull in the gas light, some of them showing the fine spiral grooves that a stylus had pressed into their surface during earlier trials. Hand-cranked mechanisms, the rotating assemblies that would drive the cylinder past the recording stylus at consistent speed, were arranged in various stages of assembly and disassembly, their gears and shafts representing the mechanical challenge of maintaining uniform rotation by hand. Coils of copper wire occupied the spaces between these components, along with the small diaphragm assemblies, thin membranes stretched across circular frames that would translate sound vibrations into the mechanical movement of the stylus needle. The first phonograph was a physically modest object, and its modesty was part of what made its achievement so astonishing. The rotating tinfoil drum sat at the center of the mechanism, its surface prepared to receive the impressions that the stylus would press into it as the drum turned. The stylus itself was a delicate needle, connected through a small lever to the diaphragm, a membrane so thin and responsive that the pressure waves of a human voice, transmitted through air, were sufficient to move it, and through it to move the needle against the tinfoil surface. The small horn of polished brass through which sound would be directed toward the diaphragm, and through which reproduced sound would later emerge, gave the device its most recognizable visual element, a gleaming funnel shape that concentrated and directed acoustic energy with elegant simplicity. The atmosphere of the laboratory on the night of the first successful recording has been reconstructed from the accounts of those who were present. The gas lamps hissed their steady background note. The cold air moved through the wall gaps with its quiet persistence. The chemical smell of the laboratory, acids and solvents, machine oil and carbon compounds, filled the space with its complex, industrial character. Edison turned the crank of the mechanism, spoke into the horn, and the stylus pressed its pattern into the tinfoil surface. Then the cylinder was returned to its starting position, the playback stylus engaged, and the crank turned again. What emerged from the horn was Edison's own voice, thin and mechanical, but unmistakably present. The nursery rhyme, "Mary had a little lamb," reproduced by a machine from a physical record of its own acoustic vibrations. The effect on those present was, by multiple accounts, one of genuine shock. The phonograph represented something qualitatively different from the telegraph or the telephone. Those devices transmitted sound across distance, but they did not preserve it. The phonograph captured time itself, or at least a fragment of it, and played it back on demand. Sound, which had always been the most ephemeral of human experiences, present for a moment and then gone forever, could now be fixed, stored, and retrieved. The implications were so vast that they were difficult to process in the moment of first encounter. News of the phonograph spread with a speed that reflected both the genuine novelty of the device and the already established reputation of its creator. Hordes of reporters descended upon Edison's home and laboratory at Menlo Park, filling the muddy lane outside the compound with the carriages and notebooks of the press. Huge audiences came to see traveling demonstrations of the new and wondrous device, marveling at the mechanical voice emerging from the polished brass horn. Edison was invited to Washington, D.C., to showcase the phonograph to an astounded Congress, and the reception there confirmed what the press coverage had already suggested. This was not merely a technical curiosity, but a genuine transformation of human capability. The Wizard of Menlo Park, as the press had begun to call him, named for the New Jersey town where he lived and worked, had produced something that defied easy categorization. The phonograph's triumph was still fresh when Edison turned the laboratory's attention toward a problem of even greater consequence. The electric light had been a subject of scientific investigation for decades before 1878, and arc lighting systems already existed. The harsh, blue-white carbon arc lights that illuminated the Menlo Park laboratory itself at night were a working example of electrical illumination. But arc lights were unsuitable for domestic or office use. They were too bright, too hot, too demanding of maintenance, too dangerous for enclosed spaces. What the world needed, and what Edison announced his intention to provide, was a subdivided electric light, a small, controllable, safe source of incandescent illumination that could replace the gas jet in every home and office in the industrialized world. The transformation of the Menlo Park laboratory that followed this announcement was remarkable in its intensity. The compound shifted from the relatively open experimental atmosphere of the phonograph period into something more focused, more pressured, and more systematically organized around a single objective. The glass-blowing facility became one of the most critical spaces in the entire operation. Its furnace roared with a heat that was physically oppressive in summer and welcome in winter, the molten glass glowing orange and white as it was gathered on the blowpipe and shaped with practiced precision. The bulb envelopes that the glassblowers produced, small, pear-shaped vessels of remarkable thinness and uniformity, were the physical containers within which the crucial experiments would take place. Each one represented hours of skilled labor, and each one was potentially destroyed in the course of a single experiment. Adjacent to the glass-blowing facility, the vacuum pump room operated with its own distinctive sensory character. The pumps themselves were mechanical devices of considerable complexity, their rhythmic breathing filling the room with a sound that was almost organic. The slow, steady evacuation of air from the glass envelopes, measured against the mercury barometers that tracked atmospheric pressure with precise, graduated columns of silver liquid. The goal was to remove as much air as possible from the interior of each glass bulb, creating the near-vacuum conditions within which a heated filament could glow without oxidizing and burning away in seconds. The mercury barometers along the wall of the pump room were read constantly, their measurements recorded in the laboratory notebooks that documented every stage of the experimental process. The search for a suitable filament material consumed the laboratory through 1878 and into 1879 with an intensity that has become one of the defining narratives of American invention. The experimental logic was straightforward. Find a material that could be heated to incandescence by electrical current, that would survive in a vacuum environment, and that would maintain its integrity long enough to be practically useful. The execution of that logic required testing an extraordinary range of materials. Platinum and its alloys, various carbon compounds, carbonized organic materials of every description. The laboratory notebooks from this period record the systematic progression through candidate materials with the methodical patience of a scientific operation that understood failure as information rather than defeat. The carbon shed took on heightened importance during this period. Carbon was emerging as the most promising filament material, and the preparation of carbon in its various forms, carbonized thread, carbonized paper, carbonized plant fibers, required the particular dark, sooty environment of the carbon shed, its walls and floor blackened with accumulated carbon dust, its atmosphere thick with the particulate evidence of the work being conducted there. Workers emerged from the carbon shed with darkened hands and faces, carrying the carefully prepared filament materials to the main laboratory where they would be mounted in glass envelopes and subjected to the vacuum pump's evacuation process. The climax of this extended experimental campaign arrived in October 1879. The specific date most commonly cited is October 21st, though the experimental record suggests that the successful demonstration was the culmination of a process rather than a single discrete moment. What is documented is the result. A carbonized cotton thread filament mounted within an evacuated glass envelope, connected to an electrical circuit and heated to incandescence, glowed with a steady, warm light for a duration that demonstrated practical utility. The laboratory at night provided the setting for this achievement, the surrounding darkness of the New Jersey countryside pressing against the laboratory windows, the gas lamps dimmed or extinguished to allow the quality of the electric light to be properly assessed, the single glass bulb glowing with a warmth and steadiness that distinguished it from every previous attempt. The light that emerged from that bulb was qualitatively different from the harsh blue-white of the carbon arc lights that had illuminated the laboratory's exterior. It was warm, amber-tinged, intimate in scale, a light that resembled, in its color, temperature, and intensity, the oil lamps and gas jets it was destined to replace, but without their heat, their smell, their constant demand for fuel and maintenance. The contrast between that single glowing bulb and the ancient darkness surrounding the Menlo Park compound on an October night in 1879 was not merely a technical contrast. It was the visible boundary between two eras of human experience, the long darkness of every night since the beginning of human history, and the illuminated world that was about to begin. A single glowing bulb in a rural New Jersey laboratory was a miracle of science, but a miracle confined to one building, on one experimental bench, serving one inventor's demonstration purposes, was not yet a transformation of the world. The distance between that October night in 1879 and the moment when electric light would become a practical reality for ordinary people living ordinary lives in ordinary buildings was not merely a technical distance. It was an organizational, financial, and infrastructural distance of staggering complexity. Crossing it would require Edison to think not as a laboratory experimenter, but as an urban engineer, a utility builder, and an industrialist operating at a scale that had no precedent in the history of electrical science. Lower Manhattan in the early 1880s was one of the densest, most chaotic urban environments in the Western world. The streets of the financial district, Wall Street, Fulton Street, Broadway in its southern reaches, were colonial-era lanes, never designed for the volume of commerce they now carried. Cobblestones worn smooth by decades of iron-rimmed wagon wheels formed the road surfaces, their irregular joints collecting horse manure and rainwater in roughly equal measure. The buildings that lined these streets were multi-story commercial structures of brick and cast iron, their facades pressed close to the narrow sidewalks, their upper floors housing the counting rooms and offices of banks, insurance companies, and trading houses that collectively managed a significant fraction of American commerce. At street level, delivery wagons competed for passage with pedestrians, pushcart vendors, and the occasional private carriage. The whole mass of urban movement producing a continuous noise of iron wheels on stone, horse hooves, shouted instructions, and the general percussion of a city conducting its business at full intensity. The lighting of this environment after dark was provided almost entirely by gas. Gas lamp posts lined the major streets, their yellow-orange flames enclosed in glass globes that cast pools of warm but limited light onto the cobblestones below, leaving the spaces between posts in relative shadow. The interiors of the commercial buildings were lit by gas jets mounted on walls and ceilings, their flames hissing softly. their light adequate for reading and writing, but accompanied by heat, the faint smell of combustion products, and the constant low-level risk of fire in buildings where paper documents were the primary medium of commerce. The gas infrastructure that served Lower Manhattan was itself a substantial industrial system. Miles of underground pipes carrying coal gas from manufacturing facilities to the distribution network, the whole system representing a significant capital investment and a powerful incumbent interest that would not welcome competition. Edison had identified the financial district of Lower Manhattan as the ideal location for his first commercial electrical system with characteristic strategic intelligence. The concentration of wealthy commercial tenants in a small geographic area meant that the revenue potential per mile of distribution cable was higher than anywhere else in the country. The presence of influential figures, J.P. Morgan among the most prominent, who were both potential customers and potential investors, gave the project a financial and social credibility that a demonstration in a less prestigious neighborhood could not have provided. And the density of the built environment, paradoxically, simplified certain aspects of the distribution problem by concentrating the load within a small radius. The building at 255-57 Pearl Street, selected as the site of the central generating station, was a pair of derelict commercial structures in the heart of the target district. The buildings required substantial reconstruction before they could serve their intended purpose. The floors had to be reinforced to bear loads far beyond anything their original construction had contemplated. The basement and ground floor had to be reorganized around the specific requirements of steam boilers and electrical generating equipment. The exterior walls, though retained, enclosed an interior that was essentially rebuilt from the ground up, a process that required months of construction work conducted in the middle of a functioning urban neighborhood, the noise and disruption of heavy construction adding to the general chaos of Pearl Street's daily commerce. The jumbo dynamos that would occupy the generating floor of Pearl Street Station were among the largest electrical machines yet constructed. Each one weighed approximately 27 tons, a mass of copper windings and iron frames that required the reinforced concrete floor specifically engineered to support it. The copper windings of each dynamo represented a substantial quantity of the metal, their gleaming reddish surfaces catching the light of the electric arc lamps that illuminated the station interior. The iron frames were bolted directly to the floor with heavy anchor bolts, the connection between machine and building designed to manage the considerable vibration that the rotating machinery would generate in operation. 6 of these machines would eventually occupy the generating floor, their combined output sufficient to serve the initial distribution network. The boiler room occupied the lower level of the Pearl Street Station, and its atmosphere was one of concentrated industrial intensity. 6 coal-fired boilers generated the high-pressure steam that drove the engines connected to the dynamos above. The coal, anthracite, chosen for its high energy density and relatively clean combustion, arrived by wagon from the street, shoveled through ground-level openings into the fuel storage area, and from there moved by hand into the boiler fireboxes in a continuous cycle of physical labor. The heat radiating from the boiler fronts was intense enough to make the boiler room uncomfortable even in winter, and in summer the conditions approached the genuinely punishing. Gauges and pressure valves lined the brick walls in rows, their needles and indicators providing the constant feedback that the boiler operators needed to maintain safe operating pressures. The hiss of high-pressure steam at relief valves, the rhythmic thud of the feed pumps, and the roar of combustion in the fireboxes combined into a sensory environment of overwhelming industrial power. The underground cable network that would carry electrical current from Pearl Street Station to its customers represented perhaps the most complex and least visible element of the entire system. Miles of copper wire, insulated with a compound of linseed oil and paraffin developed specifically for this application, were laid in iron conduits beneath the cobblestones of the financial district. The installation required opening the streets, a process that brought Edison's construction crews into direct conflict with the existing underground infrastructure of gas pipes, water mains, and the various other conduits that already occupied the subsurface of Lower Manhattan. The work proceeded block by block through 1881 and into 1882, the iron conduits carrying their copper conductors threading invisibly beneath the hooves of delivery horses and the wheels of commerce above, an infrastructure of the future being installed beneath the physical surface of the present. The technical challenges of the distribution system went beyond the physical installation of cables. The design of a network capable of delivering consistent voltage to customers at varying distances from the generating station required solutions to electrical engineering problems that had not previously been encountered at this scale. Edison's approach, the use of a three-wire distribution system that improved efficiency compared to simpler two-wire arrangements, reflected the depth of engineering thought that had gone into the Pearl Street project. The feeder cables carrying current from the station to distribution points, and the service cables running from those points to individual buildings, were sized and configured according to calculations that Edison and his engineering staff had worked through with careful attention to the economics of copper consumption. By the summer of 1882, the Pearl Street station was approaching operational readiness. The dynamos had been installed and tested. The boilers had been fired and their steam systems checked. The underground cable network extended through the target district, its conduits reaching the basements of the commercial buildings that had signed up as initial customers. The wiring within those buildings had been installed by Edison's crews. The internal distribution systems that would carry current from the service entrance to the individual lamp fixtures, each building's interior transformed into a node of the emerging electrical network. September 4, 1882, arrived with the particular quality of a day that would be remembered. Edison himself was present at Pearl Street Station as the generating equipment was brought to full operational status. The dynamos turned, their copper windings cutting through magnetic fields, generating the direct current that flowed outward through the underground cables into the financial district above. At 23 Wall Street, in the offices of J. P. Morgan's banking house, the moment of switching was marked by the appearance of incandescent light, warm, steady, amber-toned illumination, replacing the yellow hiss of gas jets that had lit those rooms for years. The quality of the light was immediately apparent to those present. Where gas flames flickered with the slight instability of combustion, the electric bulbs burned with an unwavering steadiness. Where gas produced heat and the faint smell of combustion, the electric light produced neither. The transformation of the room's nighttime atmosphere was not dramatic in the manner of theatrical spectacle. It was quiet, immediate, and absolute. The district served by Pearl Street Station on that first day of operation was modest in geographic extent, roughly 1 square mile of Lower Manhattan, served by an initial complement of customers whose combined load represented a fraction of what the system would eventually carry. But the significance of what had been achieved was not measured in square miles or customer counts. Pearl Street Station was the world's first central electrical power station, the first demonstration that electricity could be generated at a central facility and distributed through an underground network to multiple customers simultaneously, in a form suitable for domestic and commercial use. Every electrical utility that exists anywhere in the world today is, in its fundamental organizational logic, a descendant of what Edison built on Pearl Street in 1882. The physical environment of Lower Manhattan had been permanently altered by something that was almost entirely invisible: the underground cable network threading beneath its streets, the current flowing silently through copper conductors insulated with linseed oil and paraffin, the connection between a boiler room on Pearl Street and the lamp fixtures in offices throughout the financial district. The cobblestones above looked exactly as they had before. The buildings retained their cast-iron facades and their colonial-era street alignments. But beneath the surface, and within the illuminated rooms above, something fundamental had changed. The ancient rhythm of human life organized around the availability of natural light. The compression of productive activity into daylight hours, the retreat into oil lamp dimness after dark, had encountered its most serious challenge yet. The electric city had begun. By the late 1880s, the electrical landscape of America had fractured into two competing visions, each expressed not merely in technical specifications and patent filings, but in the physical geography of an entire industrial civilization being built from scratch. The conflict that historians would later call the War of Currents was not fought in courtrooms alone, nor in newspaper columns, nor in the public demonstrations that each side staged with theatrical calculation. It was fought in the brick and iron architecture of generating stations, in the wooden poles carrying high-tension wires across open countryside, in the transformer housings bolted to utility poles in residential neighborhoods, and in the vast manufacturing floors where the machinery of electrical civilization was being produced at industrial scale. Edison's direct current infrastructure had, by this point, established itself across dozens of American cities. The physical character of that infrastructure was deeply familiar. The central generating station model pioneered at Pearl Street had been replicated in city after city, each station a brick and iron fortress of boilers and dynamos occupying a substantial urban building, its coal deliveries arriving by wagon, its steam pressure maintained by round-the-clock labor, its distribution network threading through underground conduits beneath the surrounding streets. The fundamental limitation of this architecture was geographic. Direct current, operating at the relatively low voltages that Edison's system employed, could not be transmitted efficiently over distances greater than roughly 1 mile from the generating station without unacceptable losses in the copper conductors. Each station therefore served a limited radius, and extending electrical service beyond that radius required building another station. The economics of this model demanded dense urban populations to justify the capital investment, and it left the vast majority of American territory, the farms, the small towns, the industrial sites located at distances from city centers, entirely beyond the reach of electrical power. The alternating current system that George Westinghouse was deploying with increasing confidence operated according to a fundamentally different physical logic. Alternating current could be transformed, stepped up to very high voltages for long-distance transmission, then stepped back down to safe levels for distribution and use. This transformability meant that a single generating station could serve a territory of many miles, its high-tension transmission lines stretching across open countryside on wooden poles, the landscape itself becoming the medium through which electrical power moved. The Westinghouse manufacturing complex in Pittsburgh was the industrial heart of this competing vision. Its vast brick factory floors hummed with the production of transformers, alternating current generators, and the associated equipment of a system designed for geographic reach rather than urban density. The smell of transformer oil, a distinctive, slightly sweet petroleum product used to insulate and cool the iron cores of transformers, permeated the factory environment, mixing with the hot copper smell of winding rooms where miles of insulated wire were wound onto transformer cores with machine precision. The high-tension testing laboratories within the Pittsburgh complex were environments of controlled electrical drama. The air itself seemed charged in these spaces, where sparks leaped between electrode terminals during equipment testing, the sharp crack of electrical discharge punctuating the industrial background noise, the smell of ozone sharp and persistent. Nikola Tesla's contributions to the alternating current system had provided Westinghouse with the theoretical and practical foundations for a polyphase system of extraordinary capability. The patents that Tesla had developed and that Westinghouse had licensed represented intellectual property of enormous commercial value, and the physical machinery that embodied those patents was being manufactured in Pittsburgh and deployed across an expanding territory of American cities and industrial sites. The contrast between the two systems was visible in the landscape itself. Edison's urban fortresses of direct current generation standing in dense city centers, and the Westinghouse transmission lines moving across open country with the long-legged stride of wooden poles carrying copper wire toward destinations that Edison's system could never reach. Edison's response to the competitive threat from alternating current included a campaign of public persuasion that took a particularly grim form. His argument centered on the higher voltages at which alternating current systems operated, voltages that were, in fact, genuinely dangerous if improperly handled. To demonstrate this danger in the most visceral terms possible, Edison and his associates arranged public demonstrations in which animals were electrocuted using alternating current. The spectacle intended to fix in the public mind an association between AC electricity and lethal danger. These demonstrations took place in various locations, their physical settings, the bare ground, the improvised electrical apparatus, the assembled witnesses, carrying an atmosphere of calculated grimness that reflected the desperation underlying Edison's position. The campaign was, by most historical assessments, both ethically troubling and strategically counterproductive, drawing attention to the dangers of high-voltage electricity without successfully preventing the adoption of the more capable system. The most consequential deployment of alternating currents association with lethal voltage came through an entirely different channel. The state of New York, seeking a more humane method of execution than hanging, had established a commission to investigate electrical execution, and the resulting development of the electric chair drew directly on the public discourse about electrical danger that the war of currents had generated. The facilities at Auburn Prison and Sing Sing Prison in New York became the grim physical settings where this technology was developed and deployed. Auburn Prison, a severe stone structure in upstate New York, was the site of the first execution by electric chair on August 6, 1890. The condemned man, William Kemmler, dying in a chamber whose institutional architecture and clinical electrical apparatus represented the darkest possible application of the technology that was simultaneously transforming American cities with light and power. The electric chair used alternating current, and the association that Edison had sought to create between AC electricity and death was thus literalized in the most disturbing way imaginable, though the episode ultimately did little to slow the adoption of the more capable system. The decisive confrontation between the two systems arrived in Chicago in 1893 at the World's Columbian Exposition, the great fair organized to celebrate the 400th anniversary of Columbus's arrival in the Americas. The exposition's physical environment was itself an extraordinary achievement of urban construction. The White City, as the fairgrounds along the Lake Michigan shoreline came to be known, was a landscape of neoclassical buildings constructed in white-painted staff, a mixture of plaster, cement, and fiber, arranged around a central lagoon with an architectural grandeur that drew millions of visitors from across the country and the world. The scale of the electrical installation required to illuminate this environment was unprecedented. 100,000 incandescent bulbs were deployed across the fairgrounds, their combined illumination transforming the White City's nighttime appearance into something that most visitors had never imagined possible. Entire neoclassical facades outlined in electric light, the lagoon surface reflecting the illuminated buildings in shimmering double, the darkness of the Chicago lakefront pushed back by a brilliance that seemed to belong to a different and more luminous future. The Westinghouse alternating current generators that powered this spectacle hummed in the hall of machinery, their scale and output representing a demonstration of AC capability that no amount of newspaper argument could match. The contract to illuminate the exposition had been awarded to Westinghouse over Edison's competing bid, partly on the basis of cost and partly on the demonstrated capability of the AC system to handle the enormous electrical load that the fair required. The physical presence of those generators, their iron housings, their rotating fields, the transmission infrastructure connecting them to the distribution network throughout the fairgrounds, was the most persuasive argument that alternating currents advocates could have made. Millions of visitors experienced the result directly, walking through illuminated fairgrounds at night, their faces lit by the warm glow of incandescent bulbs powered by a system that Edison had spent years arguing was too dangerous for public use. The war of currents ended not with a formal declaration, but with the gradual acknowledgement of physical and economic reality. Alternating current's ability to transmit power over long distances, to serve territories that direct current systems could never reach economically, and to handle the growing electrical loads of an industrializing nation proved decisive. Edison's own company, General Electric, formed through the merger of Edison General Electric with Thomson Houston in 1892, eventually began manufacturing alternating current equipment, the commercial logic of the marketplace overriding the personal convictions of the man whose name the company no longer carried. The industrial landscapes of America were transformed accordingly. The long-distance transmission lines multiplied across the countryside. The transformer stations appeared at the edges of towns and cities, and the geographic reach of electrical power expanded from the dense urban cores, where Edison's system had first demonstrated its possibilities, to the broader American territory that alternating current could serve. The brick and iron fortresses of direct current generation did not disappear overnight, but they were joined and eventually superseded by a different kind of electrical infrastructure, one whose most characteristic feature was not concentration, but reach, not the urban fortress, but the transmission line stretching toward the horizon. By 1887, Thomas Edison had already changed the world twice, once with the phonograph and once with the incandescent light bulb, and he was not finished. The Menlo Park laboratory that had produced those achievements was behind him, its white clapboard buildings gradually falling into disuse as Edison's attention shifted toward the commercial deployment of his electrical systems. What he needed now was not the intimate experimental environment of a rural compound, but something larger, more capable, and more deliberately organized. A research facility equal to the ambitions of a man who had come to understand invention not as inspiration, but as industrial process. He found the location in West Orange, New Jersey, and what he built there would redefine what a research institution could be. The physical landscape of West Orange in the late 1880s occupied a particular register in the geography of the northeastern United States. The town sat in the foothills below the Watchung Mountains, whose wooded ridgelines rose to the west with the gentle authority of ancient geology, their slopes covered in second-growth hardwood forest that turned amber and crimson each October, before settling into the grey-brown winter palette of bare branches against pale sky. The Llewellyn Park residential development occupied the higher ground nearby, a planned community of substantial Victorian houses set among landscaped grounds, its winding roads and mature trees expressing the aspirations of prosperous families seeking distance from the noise and density of Newark and New York. Edison had purchased Glenmont, a handsome Queen Anne mansion within Llewellyn Park, as his family residence, and the proximity of home to laboratory reflected his understanding that the boundary between his domestic and professional lives was, at best, a polite fiction. Valley Road ran below the residential hillside, and it was here, on a substantial parcel of relatively flat ground, that Edison's new complex took shape through 1887. The construction proceeded with the purposeful speed that characterized everything Edison undertook when he had made up his mind about what he wanted. The main laboratory building rose first, a massive three-story brick structure of 250 feet in length, its red brick walls and large industrial windows announcing its function without ambiguity. This was not a building that aspired to architectural elegance. It was a building that aspired to capability, and every decision in its design reflected that priority. The brick construction offered fire resistance that the wooden clapboard of Menlo Park had never provided, a practical consideration for a facility where chemical experiments and high-temperature processes would be conducted continuously. The scale of the structure dwarfed anything Edison had previously worked in, its 3 floors providing a vertical organization of function that the single-story sprawl of Menlo Park had never achieved. The ground floor of the main building was devoted to heavy machinery and chemical processing, the industrial foundation upon which the more refined experimental work of the upper floors depended. Machinery of various descriptions occupied this level, its vibration transmitted through the brick walls and concrete floor, a constant low-frequency presence that workers in the building came to accept as part of the environment's character. Chemical processing. Equipment occupied dedicated areas, their fume hoods, relatively primitive by later standards, but functional, drawing the vapors of acid reactions and solvent evaporation upward and away from the working spaces. The smell of the ground floor was the smell of serious industrial chemistry, sharp, complex, and persistent, the kind of atmospheric quality that embedded itself in clothing and was still detectable hours after leaving the building. The upper floors housed the intellectual infrastructure of the operation. The library that occupied a substantial portion of the upper level was stocked with a collection of books and periodicals that reflected Edison's voracious and systematic approach to research. Tens of thousands of volumes lined the shelves, scientific journals from Europe and America, technical reference works, patent publications, and the broader literature of natural philosophy and applied science that Edison had been accumulating throughout his career. The collection was not decorative. It was a working research tool, consulted regularly by Edison and his staff as they approached new problems, establishing what was already known before committing resources to experimental work. The periodicals arrived regularly from publishers across the industrialized world, their pages representing the current state of scientific and technical knowledge in dozens of fields simultaneously. Skylights mounted in the roof of the main building flooded the drafting rooms with natural light during the working day, a practical solution to the challenge of providing adequate illumination for the detailed technical drawing that invention required. The drafting tables beneath these skylights were perpetually covered with schematic drawings in various stages of completion, the visual language of invention rendered in pencil and ink on large sheets of drafting paper. The quality of light in these rooms had a particular character, diffuse, even, and consistent in a way that the direct sunlight of south-facing windows could never achieve, and it made the drafting rooms among the most pleasant working spaces in the entire complex. Surrounding the main building, 4 smaller laboratory structures were arranged with the deliberate logic of a purpose-built research campus. Each served a specific experimental function, and the physical character of each reflected its purpose with the directness of industrial architecture. The chemistry laboratory was the most atmospherically intense of the 4, its rows of reagent bottles arranged on shelving that lined every available wall surface, its fume hoods drawing the products of chemical reactions upward through ventilation shafts, its workbenches scarred with the accumulated evidence of years of experimental work. The smell of the chemistry laboratory was the most complex and persistent in the entire complex, a layered mixture of acids and organic solvents, metallic compounds and biological materials, the chemical signature of a facility where hundreds of different substances were handled, combined, and transformed on any given working day. The physics laboratory occupied a different sensory register. Precision optical instruments, spectroscopes, interferometers, photometers, and the various specialized devices that physical measurement required were arranged on vibration-isolated benches designed to protect delicate measurements from the mechanical noise that permeated the rest of the complex. The atmosphere of the physics laboratory was quieter and more controlled than the chemistry building, its work demanding the kind of careful, patient measurement that required stillness and concentration. The metallurgy laboratory, by contrast, was dominated by its furnaces, heat-producing equipment whose radiant output made the space uncomfortable in warm weather and welcome in cold, their interiors reaching temperatures sufficient to melt and analyze metals of various compositions. Spectrographic equipment lined one wall of the metallurgy laboratory, its prisms and photographic plates capturing the characteristic emission spectra of heated metals, translating the colors of flame into the precise language of elemental analysis. The pattern shop completed the quartet of smaller buildings, and its function was the translation of experimental ideas into physical form. Wooden models of new inventions were constructed here by skilled craftsmen working from the schematic drawings produced in the main building's drafting rooms, three-dimensional realizations of two-dimensional concepts, objects that could be held and examined and modified before the commitment of more expensive materials and manufacturing processes. The smell of the pattern shop was the most benign in the entire complex. Fresh-cut wood and sawdust, wood glue and finishing compounds, the pleasant organic scent of a skilled carpentry operation. The models produced here ranged from rough approximations intended to test basic spatial relationships to refined objects of considerable craftsmanship, their wooden surfaces shaped and finished to a quality that allowed detailed assessment of mechanical function. In 1893, a structure of entirely different character appeared on the West Orange property. The Black Maria, named by Edison's workers for the dark, cramped police wagons that the building's shape and color supposedly resembled, was the world's first film production studio, and its physical form was unlike anything that had previously existed. The building was covered in black tar paper, its exterior absorbing rather than reflecting light. Its interior walls painted the same deep black to prevent unwanted reflections from interfering with the photographic process. The structure was built on a pivot, a rotating mechanism that allowed the entire building to be turned on its base, tracking the movement of the sun throughout the day so that the open roof section, a long slot running the length of the building, could maintain its orientation toward the light source. The mechanical ingenuity of this arrangement was characteristic of Edison's approach to practical problems. Identify the requirement precisely, then engineer a solution that meets it directly. The interior of the Black Maria was a cramped black-walled stage of remarkable atmospheric intensity. The single performer's platform, positioned beneath the open roof slot, was bathed in brilliant New Jersey sunlight that poured down through the opening with a directness and intensity that indoor lighting of the era could not approach. The massive kintograph camera mounted on its heavy iron stand occupied a fixed position relative to the performance area. Its film transport mechanism and optical system, designed to capture the movement of performers with sufficient clarity and speed to create the illusion of motion when the resulting film strip was played back through the kinetoscope. The rest of the interior remained in deep shadow, the contrast between the brilliantly lit performance area and the surrounding darkness giving the Black Maria a theatrical quality that was entirely functional rather than decorative. Far from the lone genius myth that popular culture had already begun constructing around Edison, the West Orange complex functioned as one of the world's first true industrial research laboratories, a place where invention was systematic, collaborative, and constant. According to Paul Israel of the Thomas Edison papers, there was something about Edison that embodied a particular vision of American inventive character: self-taught, direct, simultaneously practical and visionary. That quality attracted talented people, and the West Orange complex at full operational capacity was a concentration of technical skill and experimental energy that had no equivalent in the private sector anywhere in the world. The sensory portrait of the West Orange complex in full operation was overwhelming in its industrial richness. The constant noise of machinery on the ground floor of the main building, the rhythmic turning of lathes, the percussion of metalworking equipment, the mechanical breathing of pumps and compressors, formed a baseline of industrial sound that permeated the entire property. Chemical smells drifted from the open windows of the chemistry laboratory on warm days, their complex mixture carrying across the property boundary and into the surrounding neighborhood, an olfactory announcement of the work being conducted within. Electric lights burned through the night in the main building's upper floors, their warm glow visible from Valley Road below, a beacon of concentrated intellectual activity that recalled the carbon arc lights of Menlo Park a decade earlier, but expressed a different order of ambition. The railroad siding that connected the West Orange complex to the broader transportation network completed the picture of an industrial operation fully integrated into the commercial infrastructure of the era. Supplies arrived along this siding, chemicals and raw materials, precision instruments ordered from manufacturers in America and Europe, the bulk commodities of industrial research consumed in quantities that required freight delivery. Finished products departed along the same route: phonographs and their components, motion picture equipment, the manufactured outputs of an invention factory that had learned to move from experimental demonstration to commercial production with a speed and efficiency that no previous research institution had achieved. West Orange was not merely a laboratory. It was the physical embodiment of a new idea about how human ingenuity could be organized, resourced, and directed, an idea whose influence on the institutions of research and development that followed it would prove as lasting as any of the specific inventions produced within its brick walls. Inside the Black Maria, the world's first motion picture studio, light itself, became the raw material of a new art form, and the physical environment that Edison and his assistant William Dickson constructed to capture it was as deliberately engineered as any dynamo or vacuum pump that had come before it. The interior of the Black Maria in the early 1890s was a space of extraordinary sensory contrast. The rough wooden floor planking, darkened with use and worn smooth along the paths that performers and technicians traveled most frequently, ran the full length of the building beneath a ceiling of black painted timber. The walls absorbed light rather than reflecting it, their tar paper exterior and dark interior surfaces creating an environment of almost total shadow, except in one critical location: the performance platform positioned directly beneath the open roof slot. Here, brilliant New Jersey sunlight poured downward with an intensity and directness that no artificial lighting system of the era could have replicated. The light fell onto the performance area in a concentrated column, illuminating performers with a clarity and sharpness that the kintograph, camera's photographic emulsion, required to capture movement at the necessary speed. The kintograph camera itself occupied a fixed position on its heavy iron stand, its bulk and weight expressing the mechanical complexity within. Edison and Dickson had developed this camera through sustained experimental work beginning in the late 1880s, working toward a system that could photograph movement in rapid sequential frames on a continuous strip of film. The camera's film transport mechanism advanced the celluloid strip in precise increments, each frame exposed for a fraction of a second before the next was positioned behind the lens. The sound of the kintograph in operation was distinctive, a rhythmic mechanical clicking that marked each frame's exposure, the sound of time being divided into discrete photographic slices. The smell of the chemical emulsion on the film stock mixed with the machine oil that lubricated the transport mechanism, adding to the Black Maria's already complex atmospheric character. Performers who entered the Black Maria for filming encountered an environment unlike any theatrical stage they had previously known. Vaudeville acts, boxing demonstrations, animal performances, and various novelty entertainments were among the subjects filmed in the studio during its operational years. The performers stood in the brilliant column of sunlight, while the surrounding interior remained in deep shadow, a spatial arrangement that inverted the normal theatrical relationship between performer and audience. There was no audience here, only the mechanical eye of the kintograph, recording movement for later reproduction through the kinetoscope viewing machines that would carry these images to paying customers across American cities. The kinetoscope parlors that proliferated across American cities beginning in 1894 represented the first public environment specifically designed for the consumption of moving images. The first commercial kinetoscope parlor opened on Broadway in New York City in April 1894, and its storefront interior established the template that subsequent establishments would follow. Rows of wooden peephole viewing machines lined the walls and filled the floor space. Each machine a cabinet of polished wood, housing the mechanical and optical system within. A small electric bulb illuminated the interior of each cabinet, its warm glow visible through the viewing aperture at the top of the machine. The mechanical clicking of the film transport mechanism, the same rhythmic sound that had characterized the kintograph in the Black Maria, filled the parlor with a constant low-level percussion, each machine cycling its brief loop of film continuously throughout the operating day. The smell of the kinetoscope parlor was particular and memorable to those who experienced it. Machine oil and the faint warmth of electric bulbs, the slight chemical tang of the film's stock circulating through the transport mechanisms, the accumulated breath and presence of the customers who bent over the viewing apertures throughout the day. The experience of viewing was intensely private despite the public setting. Each customer bent forward to press their eyes against the viewing aperture, the surrounding parlor disappearing as their vision filled with the moving images within the cabinet. What they saw lasted only seconds, the brief film loops capturing moments of movement, a dancer's performance, a boxing match's exchange, a sneeze rendered in magnified detail. But the effect was consistently described by early viewers as astonishing, a window onto captured reality that seemed to defy the ordinary boundaries of human experience. The broader urban entertainment landscape, into which Edison's motion picture technology arrived, was already rich with competing attractions. The vaudeville theaters of Broadway and 14th Street in Manhattan were established institutions of popular entertainment, their stages hosting variety performances that drew audiences from across the social spectrum. These theaters were environments of considerable atmospheric complexity, their interiors ornate with carved woodwork and painted plasterwork, their gas and early electric lighting creating warm pools of illumination above the audience, the smell of grease paint and sawdust mixing with the accumulated presence of hundreds of patrons. The kinetoscope parlors initially existed alongside rather than within these theatrical environments, offering a different and more intimate form of moving image experience. The transition from the peephole kinetoscope to projected moving images, a development that Edison initially resisted but eventually embraced, transformed the social environment of early cinema entirely. When projected images appeared on white screens in darkened rooms, the solitary experience of the kinetoscope cabinet gave way to a collective one. Audiences sat together in darkness, their faces turned toward a shared illuminated rectangle, experiencing the same images simultaneously. The Nickelodeons that emerged in working-class neighborhoods across American cities in the early 20th century were the physical embodiment of this collective experience. Storefront spaces converted to screening rooms, their interiors stripped of everything except rows of wooden chairs facing a screen, admission priced at 5 cents to attract the broadest possible audience. These Nickelodeon interiors were deliberately unpretentious environments. The wooden chairs were hard and close-set. The ventilation was often inadequate, the air thick with the warmth of many bodies in an enclosed space. The projection equipment occupied a booth at the rear of the room, its mechanical operation audible throughout the screening as a rhythmic clicking that echoed the kinetoscope parlors from which the technology had descended. The projected light itself, the beam traveling from the projector lens through the darkened room to the white screen, was visible as a cone of illuminated dust particles, a physical manifestation of the technology's operation that gave early cinema screenings a quality of theatrical magic, entirely separate from the images being projected. The environments that Edison's motion picture technology created, from the Black Maria's brilliant sunlit platform to the darkened Nickelodeon storefronts of working-class neighborhoods, represented a new chapter in the long history of human storytelling. Moving images, captured in New Jersey sunlight and reproduced by mechanical and electrical systems of considerable ingenuity, had found their way into the daily lives of ordinary people across American cities, transforming the experience of leisure and the possibilities of shared imagination in ways that no one, including Edison himself, had fully anticipated when the kintograph first clicked its way through a loop of celluloid in the cramped black interior of the world's first film studio. Some legacies fade into abstraction, becoming ideas rather than places, principles rather than textures. Thomas Edison's legacy refused that fate. It remained stubbornly, insistently physical, embedded in the landscape of New Jersey, in the infrastructure of modern cities, in the preserved chemical shelves and worn wooden floors of buildings where the future was once assembled by hand. To stand in these places today is to encounter something rarer than a monument, the actual environment of transformation, preserved against the ordinary erosion of time. The contemporary landscape of Edison, New Jersey, renamed from Menlo Park in 1954 to honor the inventor who had worked there, carries its historical significance in an unusual form. Where the original laboratory complex once stood, a 131-foot concrete tower rises from the surrounding suburban terrain, its apex crowned with a replica light bulb that glows against the New Jersey sky. The tower was dedicated in 1937, the year of Edison's birth centennial, and its scale is deliberately monumental, visible from considerable distances across the flat terrain, a vertical marker in a horizontal landscape. The surrounding area has been absorbed into the residential and commercial fabric of modern New Jersey. The muddy, unpaved roads and rolling farmland of the 1870s, replaced by suburban streets and shopping centers. But the tower persists, its concrete mass anchoring the memory of what happened here to the specific geography where it occurred. The Thomas Edison National Historical Park in West Orange preserves something far more intimate than a tower. The laboratory complex on Valley Road has been maintained with the kind of careful, scholarly attention that allows visitors to encounter not merely the buildings, but the atmosphere of working invention. The main laboratory building's interior retains the chemical shelves that lined its walls. During Edison's lifetime, rows of labeled bottles, their contents long since removed or rendered inert, but their arrangement preserved as a record of the organizational logic that governed experimental work at the facility. The original machinery occupies its positions on the ground floor, its iron and steel surfaces showing the patina of decades, the mechanical complexity of late 19th century industrial equipment visible in every gear and shaft and bearing. The library on the upper floors of the main building remains perhaps the most evocative space in the entire complex. Edison's personal collection of books and periodicals still occupies the shelves, tens of thousands of volumes whose spines represent the intellectual landscape of a self-educated man who understood that systematic knowledge was the foundation of practical invention. The collection spans scientific disciplines and languages, its European journals alongside American publications, its technical reference works alongside the broader literature of natural philosophy. The drafting tables beneath the skylights are preserved in their working configuration, the quality of light falling through the glass, above unchanged from what Edison's draftsmen experienced during the facility's operational years. To stand in this library is to understand something essential about Edison's method, the conviction that invention required not merely inspiration, but information, not merely talent, but knowledge systematically acquired and applied. The Black Maria Film Studio has been reconstructed on the West Orange property, its tar paper exterior and rotating structure rebuilt to allow visitors to understand the physical logic of the world's first film production facility. The reconstruction communicates what photographs cannot fully convey: the intimacy of the performance space, the dramatic contrast between the brilliantly lit platform beneath the roof slot and the surrounding darkness, the mechanical ingenuity of a building designed to track the sun. Standing inside the reconstructed Black Maria, the relationship between the physical environment and the images it produced becomes immediately comprehensible in a way that no description can fully achieve. Beyond these preserved sites, Edison's most enduring legacy exists in a form that is simultaneously everywhere and invisible: the infrastructure of electrical civilization, that his work helped create. The power stations, transmission lines, and urban distribution networks that transformed the nighttime landscape of the industrialized world are the direct institutional descendants of Pearl Street Station and the Menlo Park experiments. Every electrical utility operating anywhere in the world today embodies, in its fundamental organizational logic, the model that Edison demonstrated in Lower Manhattan in 1882. The specific technologies have evolved beyond recognition. Alternating current long since superseded direct current for distribution. Digital controls replaced analog gauges. Renewable generation joined fossil fuel combustion. But the basic concept of centralized generation and distributed delivery remains the foundation of electrical infrastructure everywhere. The global transformation of the nighttime landscape that Edison's work initiated is perhaps the most visually dramatic expression of his legacy. Before electrical illumination became widely available, the darkness of night was a genuine environmental condition, not merely the absence of daylight, but a positive presence, a thick, encompassing darkness that shaped human behavior, compressed productive activity into daylight hours, and defined the rhythm of daily life across all of human history. The oil lamp and the candle and the gas jet had pushed back against this darkness, creating small amber pools of warmth and visibility, but they had never truly defeated it. The darkness beyond the lamp's reach remained absolute, and the lamp itself demanded constant attention, fuel replenishment, wick trimming, the management of an open flame in proximity to the combustible materials of ordinary domestic life. The world that Edison's electrical infrastructure helped create replaced this ancient darkness with something qualitatively different. The incandescent bulb, warm, steady, safe, requiring no maintenance beyond the occasional replacement, extended the productive and social hours of human life in ways that had immediate and profound effects on everything from industrial output to literacy rates to the organization of domestic space. The gas jets' hiss and smell and heat disappeared from rooms that had known nothing else for generations. The oil lamp's amber flicker gave way to the unwavering warmth of electric light. The darkness beyond the window, which had once begun at the edge of the lamp's reach, retreated before the advancing infrastructure of electrical distribution. A modern city at night is the fullest expression of what that retreat has produced. Seen from altitude, from an aircraft descending toward a major metropolitan area, or from a satellite image of the illuminated continents, the pattern of human settlement is written entirely in light. The dense cores of major cities blaze with an intensity that rivals daylight in their most concentrated areas, their commercial districts and transportation corridors outlined in electric brilliance. The residential neighborhoods surrounding those cores glow with a softer, more distributed light. The accumulated illumination of millions of individual homes, each one a node in the electrical network that connects them all to generating sources that may be hundreds of miles distant. The highways threading between cities are marked by the moving lights of vehicles traveling through the darkness, their headlamps powered by the same electrical systems that illuminate the buildings they pass. The airports, the industrial facilities, the sports stadiums, the bridges and waterways, all of them visible from above as concentrations of light against the surrounding darkness. The geography of human civilization rendered in electric illumination. This panoramic nighttime landscape is a direct environmental descendant of a single glowing bulb in a New Jersey laboratory in October 1879. The connection is not metaphorical. It is physical and historical, traceable through the specific institutions and technologies that Edison's work initiated, Pearl Street Station to the regional utility, the Menlo Park filament to the modern LED, the underground conduit threading beneath Manhattan's cobblestones to the transmission infrastructure spanning continents. Edison himself held more than 1,100 patents across his lifetime, a number that reflected not the solitary genius of popular mythology, but the systematic, collaborative approach to invention that he pioneered, building the first research and Development Laboratory in America, decades before anyone else understood the value of such an institution. The preserved environments of Menlo Park and West Orange exist as physical evidence of how that work was actually done. The chemical shelves and worn work tables, the library stocked with consulted volumes, the machinery still occupying its original positions on reinforced floors. These are not merely historical curiosities. They are the environments in which the modern world was assembled, piece by piece, experiment by experiment, in the amber glow of gas lamps that Edison himself would soon make obsolete.